Zinc-doped niobium pentoxide photocatalysts driven by visible light, an experimental and theoretical study. This paper was published in Materials Chemistry and Physics and was written by Jéssica Oliveira, Mariana Reis, Maíra Pires, Luiz Ruotolo, Teodorico Ramalho, Cauê Oliveira, Lívia Lacerda and Francisco Nogueira. Sustainable development has been subject of discussion all over the world due to the need to adopt measures that stimulate both economic growth and environmental preservation. For example, caffeic acid is an effluent from coffee processing, and it is one of the most toxic and recalcitrant phenolic compounds, being extremely harmful to aquatic systems if released into the environment. Another organic pollutant is rhodamine B, that is a wastewater from textile process negatively affecting water quality and consequently the environment and human health, mainly due to its biodegradation resistance, carcinogenic, and toxic potential. In this context, photocatalytic processes are important because they can mineralize pollutant organic effluents into non-toxic compounds, such as carbon dioxide and water, providing environmentally friendly industrial processes. Photocatalysts are materials that need illumination to be activated for decomposing organic pollutants. Niobium pentoxide is one of the most applied photocatalysts, and it is activated only under ultraviolet radiation. However, it is interesting to activate niobium pentoxide under visible light, since it would be possible to use sunlight to drive the desired reactions. This modification can be accomplished by the doping process, in which some matrix atoms are substituted by a foreign element. Zinc atoms can be a good candidate as a doping element, since it presents an ionic ratios and electronegativity similar to that of niobium. In this sense, the aim of this work was to evaluate the influence of low contents of zinc doping atoms on the photoactivity of niobium pentoxide photocatalysts. The undoped and zinc-doped niobium pentoxide photocatalysts were synthesized by the oxygen peroxide method followed by crystallization under hydrothermal conditions. It was used low contents of zinc such as 0.1% and 0.2%. The photocatalytic activities of the samples were evaluated for the photodegradation of rhodamine B and caffeic acid. In a typical procedure, 10 mg of the photocatalysts were added into the rhodamine B or caffeic acid aqueous solution. These dispersions were exposed to ultraviolet and visible radiation. The best photocatalyst for the degradation of rhodamine B was the sample containing 0.1% of zinc, degrading approximately 90% of this compound under ultraviolet radiation. On the other hand, the best photocatalyst for the degradation of caffeic acid was the sample containing 0.2% of zinc, degrading about 80% of this pollutant, also under ultraviolet radiation. It was proved theoretically and experimentally that the doped samples presented band gap energy below 3 electrovolts, therefore they could be activated under visible light. In this sense, it was observed that under visible radiation, the samples degraded almost the same amounts of rhodamine B and caffeic acid than the values obtained under ultraviolet light. Another important point is that the photodegradation percentage remained practically constant after the first cycle. The results discussed in this work indicated that small contents of zinc were enough to considerably decrease the band gap of niobium pentoxide and activate the semiconductor under visible illumination. This happens because zinc-fluorine atoms create impurity levels between the valence band and conduction band of niobium pentoxide. Therefore, less energy is needed to promote one electron from the valence band to the impurity level than from the valence band to the conduction band. However, the key factor responsible for the remarkable improvement of the sample's photoactivity is the use of very small amounts of the dopant, since excess impurities act as recombination centers and too few fluorine atoms are not able to create impurity levels in each particle of niobium pentoxide. For further details, please see the paper published in Materials Chemistry and Physics.